So let's talk about this multi-cycle data path now. You just give your response in the chat box. Okay. Here, the interesting is, which we need to understand is instruction fetching stage. Second one is instruction decode stage. Third one is instruction execution stage. Fourth one is the memory access stage. And fifth one is write back stage. Okay. So now the instruction fetching stage is common for any class of instructions. So what is there? Program counter, which holds the address of the next instruction to be executed. Based on that address, it connects to the data path connects to the instruction memory, and the adder will be used in the instruction fetching stage to compute the next instruction address. So program counter, which holds the current instruction address, that path connected to the adder 1, plus the second data path is 4 bytes connected to the first adder. So the output of these components, this adder and the memory access, will be stored into the interstage buffer. We call these bars as interstage buffer. So the ALU1 output, this adder output is the NPC that will be stored into this interstage buffer, as well as the instruction. It may be the add instruction for arithmetic instruction set, or move instructions from the memory instruction set architecture, or jump not equals to from branch instructions. So if any instruction, that will be fetched from here. The second one is instruction decode stage. So in the instruction decode stage, okay, this is very interesting, remember. Okay, let me just write add and suppose move instruction, and suppose branch instruction is comparison, and jump instruction, jump not equals to 0. So in the instruction decode stage, it decodes whether source 1 and source 2, what are the source operands for any of these instructions. Let us take the arithmetic first. So it finds source 1 register data path, then source 2 register data path, and the destination register data path. So source 1 and source 2 reads from the register file, but in some instructions, the destination will be there. That destination register identified with the register ID. So that is the destination register. And in this add instruction, suppose the second operand is the immediate value, suppose, for example, 5. Add R1 with 5. So that is the immediate value. So that data path also exists in the instruction decode stage. Clear? So after decoding this, if the immediate values are there, that means it requires another component, that is sign extender. So in the data path, this immediate data path connecting to the sign extender, another hardware component. So then the result of this sign extender, or the values which are reading from this register file, and if the destination register is mentioned like this, that identity will be stored into the interstage buffer. So that is the interstage buffer between the instruction decode stage and instruction execution stage. So it is identified as ID over execution stage. First interstage buffer is existing between instruction fetching and instruction decode stage. Right? In the execution stage, what are the components? This ALU output, that is NPCD, not yet updated in the PC, still the first instruction in the execution stage only. So in the execution stage, the instruction is going to perform this add operation, suppose. So here the interesting part, please remember, this single ALU can perform multiple operations like arithmetic operations, memory operations, and branch operations. So if it is performing arithmetic operation, in this case, the inputs are reading from register file. In this case, if the second operand is registered, the second input is not from register file, from the sign extender. So there is a possibility of two input lines here. So based on the operation, which input should be selected means the decoders are used. The decoders will be used. Okay. So for example, let us say the add instruction R1, R2, R3, and the add instruction R1, R2, and suppose 5, the value 5. Then how it will be executed? For that, the multiplexers are used. The multiplexers used. So these multiplexers takes multiple inputs and gives one output. So it takes, for the first operation, suppose the multiplexer 1 and multiplexer 2, they both select the input line from the register file. So the data path is selected by this multiplexer for this kind of operation. So next, if the and ALU performs this add operation, and if the instruction is suppose add R1, R2, 5 means source 1 is the multiplexer 1 selects the input line from register file, and multiplexer 2 selects the input line from this sign extender. That is the immediate value, not this. So for this operation, or if it is a move operation, suppose move R1, R2 plus 100, in that case, the source 1 is R2, source 2 is immediate value, that 100 will be selected. Is that clear? Does that make sense? Okay. So the output of this ALU, that will be loaded into a temporary register. Okay. That ALU output for the arithmetic operations. Okay. And the ALU output of the memory instructions are the effective address that will be loaded into this temporary register. If it is a branch instruction, so that is, let me use, okay. If it is a, it's clear, okay. Yeah. Oh, sorry. Let me just discard this. Okay, execute once again quickly. So the next one is, if it is a branch instruction, so then what is the job of this multiplexer 1 and multiplexer 2? Let us see. So for comparison operation, then it jump not equals to, suppose some 99, comparison operation is R1 and R2. So in jump, to go to this jump instruction, it is the current program counter value that generates the NPC next sequence of instruction, okay, plus the target. So it takes the first input for this ALU to build a single ALU, okay. This NPC will be given as an input. Second input is the immediate value. So the ALU that performs the branch target address, and that will be loaded into the temporary memory if the branch instructions are in the execution stage. Then comes to the memory instructions here. Okay, so in the comparison stage, this is a zero flag register which is reading from this register file. It consists of only zero value. In CPU simulator, which we observed the flag register, status flag register, whether it is zero or negative or overflow. Okay, so that value will also store based on the branch instruction into interstage buffer. So what is important takeaway from here is how these multiplexers are selecting the appropriate input line based on the instruction set. The next one is the destination register ID is still going on because the ALU is just performing the execution operation. So in the memory access stage, if there are only memory instructions, suppose like move instructions, move R1 and R2 plus suppose 100, when there are memory instructions, then the ALU output is the memory effective address. Based on this effective address, okay, the ALU output, the data memory will be accessed. And from this data memory, okay, so that is R2 plus 100. So based on this address, the data will be accessed. Okay, if it is a add instruction, add R1, R2, R3, suppose, then the ALU output is the arithmetic value here. If it is a branch instruction, suppose, like jump not equals to 99, in that case, the ALU output is the branch target address. So let us assume if it is a memory instruction, then from this memory, the data path is connecting, the data is reading from the memory, and that value will be stored temporary register. Okay, and if it is a arithmetic instruction, at this memory access stage, the value is not writing. So simply it passes this stage for the arithmetic instruction. And if in the execution stage, whatever the temporary value is there, which is adding R2 plus R3, that will be right back into the register file that is R1, suppose. So at this memory access stage, the important is at the end of this instruction execution stage, the important point here is if the ALU output is the memory access stage, then it loads the result into the R3 means register. If it is arithmetic instruction, ALU output will write into the register file in both the cases. Okay. For load instruction, reading the value from move. For the arithmetic instruction, it is directly passing to the next stage. If it is branch instruction, then another multiplexer will be used. The ALU output here is the branch target address plus it is adding with this next instruction, which is the ALU output, this ALU output. So how this will be selected means the control signal to this multiplexer 3 is based on this zero flag registers. That comes from comparison operation. So based on that, whether it will select the jump to the next instruction, okay, or it jump to the target, suppose. That will be updated. So remember here, at the end of the execution stage and during the memory access stage, this program counter will be updated. And after that, it goes through the same procedure: instruction fetching, decode, execution, memory access, and write back stage. Right? So in the last one, in write back stage, there are two results are there. Both are going to write in this register file. So the multiplexer is selecting here. So this multiplexer, if it is move instruction, then the data will be read from the data will read, suppose the value 5, the data will read from this, and that data will write into the register file in the write back stage. If it is ALU operation, that arithmetic operation, then this output line will be selected, and that will write the result back into the register file. So this is the important one: multiplexer 1, multiplexer 2, multiplexer 3, and multiplexer 4. Okay. So selecting data path is very important. Is that make sense?